Good.
Okay, so let's record. All right, so it's a great pleasure to have Irene Valenzuela from CERN in Madrid, and she'll talk about what can we learn from the absence of global symmetries. So please take it away.
Okay, thank you, Sakura, and thank you all of you for the invitation to give a talk here. So my plan is to I have prepared a talk which is mixing a few things, like to get a global idea of what can we learn from the absence of global symmetries, like what are the constraints on the EFT that arises. And I mean, I will try to start slowly. So most important thing is that if you have any question, just don't hesitate to interrupt. Okay. Okay, very good. So symmetry. So of course, this is a symmetry seminar. So I guess everyone here loves symmetries. They all agree they are very useful in physics. Especially recently, there is all this activity with new notions of symmetries that have been developed and can be useful to describe different properties of the theory, like higher force symmetries, non-invertible symmetries, and so on. So there is a beautiful amount of work on this direction. But the point is that eventually, if you want to use this to describe what's our universe, you should couple these QFTs to gravity. And then there is this common law that global symmetries cannot be exact in quantum gravity. Okay, so you could ask, okay, then what happened with all this beautiful progress, all these developments? So we should stop thinking about global symmetries. There are no symmetries in nature. What's going on? And of course, I wouldn't be giving this talk if the answer is that symmetries are not useful. Of course, they are very useful. But the message that I want to convey is that it's not only that they are useful when they are present, but also when they are broken, like when they are absent. Because by understanding exactly what are the mechanisms for which quantum gravity, in general, some theory avoids the global symmetry, like break the symmetry or gauge the symmetry, we can put constraints on the EFT dynamics and reformulate many familiar phenomena from this language of symmetries. Okay, so the point is that quantum gravity, I will explain this in more detail, but quantum gravity suggests that there are no global symmetries, and this puts constraints on the EFTs. Of course, I think this is interesting, even if you don't care about quantum gravity at all, because the point is that you can just forget about the first step and just think of the other two. And the point is that there is a very nice one-to-one correspondence between some properties of the EFT and some broken symmetry, some mechanism to break or gauge the symmetries that you can also use to classify what QFTs you can have in general. Okay, so the plan, what I'm going to do is to first review a bit what is the intuition, why we think that there are no global symmetries in quantum gravity, putting special emphasis on defining exactly what we mean with a global symmetry here. So how to properly, because the whole point is here is try to define exactly what is the symmetry that is forbidden, because it's not any symmetry. And then I will explain a bit how the symmetries can be broken or gauged, or how we can get rid of these symmetries, and provide some examples of implications that arise from this. Okay, so I will describe in more detail, for example, the completeness of the charge spectrum, and also how to understand the existence of worldvolume degrees of freedom, axions, and other string theory features as consequences of requiring the absence of global symmetries. Okay, very good. So let's start. So no global symmetries in quantum gravity. Okay, so I guess that probably all of you have heard this at least once or more than once, but it seems very vague without having a proper definition of what we mean with global symmetry. Okay, so they tell me that there are no global symmetries, so that they must be broken or gauged. And I'm going to do two things. I'm going to give you a physical intuition of what is the difference between global and gauge, and then I'm going to give you the proper definition in terms of the topological operators. So first, the physical intuition is that when we say that there are no global symmetries in quantum gravity, it doesn't mean that there are no symmetries. It just means that they must be gauged in the sense that you should be able to measure the conserved charge from very far away. Okay, so the difference between global or gates is precisely physically is this difference between whether you can access to this conserved charge even if you are at asymptotic infinity. And the idea is that the second case in which when you cannot measure this charge is what should not be allowed in quantum gravity. So we'll see it goes a bit along the lines of having some sort of holographic perspective of the world. Okay, like you should be able to carry information to the boundaries. So just to give an example, if you are in the standard model, for example, in these processes, you have two types of symmetry. You have B minus L and the electric charge, which are conserved at the level of the standard model. One of them is global because there is no way to know the value of B minus L unless you really go to the experiment and count how many baryons and leptons you have. While for the electric charge, this is a symmetry which is completely fine, but it's gauged. It's associated to a gauged degree of freedom. It's like the global part of the gauge group. And this is what I call a gauged symmetry. And this is fine. We can measure this because we have the electric field, we have a Gauss law, and we can measure the charge from far away. Okay, any question?
May I ask a basic question, maybe? Just a basic confusion. If you have a Wilson line, for example, we typically say it has a one-form symmetry, charge under one-form symmetry. And we measure it by integrating something that surrounds the Wilson line. In that case, why don't you call this measuring from far away? That would be the question.
But the thing is that you need an experiment. So like, so right now you're thinking, maybe what you have in mind is just to think of the topological operator which surrounds the Wilson line, right? Mm-hmm. And you say this is not like measuring. Like in order to measure, you need to this integral on the volume, you need to translate it to an integral on the surface, like a Gauss law, so that you have you can have an experiment and measure this charge from far away. Otherwise, there is not experiment that you can design to measure even the one-form global charge of the Wilson line. You see, it's like for the zero form, it's clear, right? Because then you can think something is localized. Okay, I have some topological operator around this defect. You would say, okay, but this is it's topological. I can just send the surface not very far away. But this is not the same. I mean, there is no. I mean, you need to design an experiment to get information of that charge. And how we do in practice for the electric charge, you can do it because then this integral on the volume becomes by a Gauss law, an integral on the surface because the current is exact. And you can, that means that you have some electric field is going far away and you can detect the charge thanks to this electric field.
But isn't that kind of the same thing we do for the Wilson line? We integrate the star F, right?
But you would need, in order to measure this, you would need that the one-form global symmetry of the Wilson line is gauged in the sense that you have a two-form gauge field, which now can carry the information of this charge of the Wilson line, because it's the global part is going to be part of the global part of this two-form gauge field, so the one-form gauge symmetry. And this then is something that you can measure far away because you have the two-form gauge field that propagates. Without it, there is no experiment that you can design to measure this, like in physical space, in space-time. Right?
I mean, well, I'm not an experimentalist, obviously, but
I agree with you. I also can understand the distinction.
Right. I could imagine that, if I want to see if somebody has put the Wilson line somewhere, there could be a huge sphere and measure integral of star F, which is gauge invariant, something like I could ideally measure somehow. It doesn't really matter where I measure it, right?
Yeah, but the thing is that if you have I mean, you're gonna get just a trivial result if you don't have the gauge field propagating, right? Because if you integrate,
well, you have the electromagnetic field which is propagating, but there's not the background field associated to the symmetry, right? It's the field that.
So think, for example, like if I have an axion, okay, I have a zero form global symmetry. Now the difference is, what is the difference between having just the axion with a zero form global symmetry, some scalar, or the scale, this zero form global symmetry being gauged by a gauge field, by a one form gauge field. Now both, I have a charge, which is the integral of d phi, right? The current associated to the shift symmetry of the scalar. And the point is that in one case, I mean, when you have the electric field, you can measure this from far away, you have the electric field and so on, you can have an experiment. But if you only have the scalar, there is no way, this is just some localized object in the middle of the bulk. There is no way to carry this information far away. How you measure the charge associated to the shift symmetry of a scalar?
I think I need to think of it. I don't want to derail your talk, so maybe we could do this later if nobody wants to just. I don't think I'm getting the difference, but I'm not sure how important it is for your talk.
No, it's just to give an intuition at the beginning. I mean, it's not very important. I'm trying to think how to explain it better.
Well, I think we do know the difference between a gauge symmetry and a global symmetry. It's just that this distinction of how you want to characterize it.
I mean, it's like this is based also like in the proof of Harlow-Naguri. I mean, like an idea CFT, right? Like that's how they do it. Like if you just have an operator that is in the bulk and it's just global, you don't have a Wilson line going to the boundary. This operator is localized in the middle of the bulk. So from the boundary, there is no boundary operator that can have the same charge. So like you have, what they do is that they have this entanglement wedge reconstruction, right? So each part of the boundary can access a part of the bulk. But if these regions are very small, in the end, you are missing part of the bulk. So you are missing the information of this defect, which is localized in the middle. And then there is no, when you have a global symmetry in the bulk, that would be inconsistent in the boundary. So because there is no way to carry that information. While if you have a global symmetry in the boundary, it means that it's gonna be gauged in the bulk. So you have a Wilson line that goes from the boundary to the middle of the bulk. And so on one side ends on the boundary and on the other side ends on the defect on the bulk. And then it's consistent. You have, okay, a global symmetry in the CFT and a global symmetry that is gauged in the bulk, and everything is fine. But without it, there is no way to access from far away that information. And I think with the picture that you have, I mean, I think what is confusing is, yeah, like the picture of the topological operator that's around the defect and so on. But the point is that then you have to be careful, because if you integrate over a closed manifold, then the result is always zero, right? So there is no, like if we are in Minkowski, and we don't have a boundary, I don't think, yeah, I don't know, I cannot think how to measure that. I don't see how I'm gonna get a non-trivial result.
Maybe this is a good topic for the discussion.
Okay, yeah, we can continue later.
Sure.
Okay, so this I mean, this was just to give you an intuition, which actually the point is that this intuition is what is behind this proof for the absence of global symmetry in quantum gravity, because as I said, like the proof of Harlow-Naguri in ADS-CFT is based on this. It's based on the difference of whether you can carry the information to the boundary or not. Also, the motivation coming from black holes is the same, because like if you have a black hole, I mean, these heuristic motivations is that if you have a global symmetry, you can construct a black hole with different values of the charge, of the global charge. But the horizon of the black hole is blind to this global charge. It only depends on the asymptotic mass or the gauge charge. So that means that from far away, the black hole looks the same, even if you have different values of the global charge. Because of the same reason, because you cannot carry this information far away. So from the black hole perspective, it's equivalent to have different values of the global charge. It's different to have different values of a gauge charge. And the heuristic motivation is that if you have then a global symmetry, you can construct different black holes with different values of the global charge that look the same. And this is going to give rise to an infinite entropy, no? Because in the end, entropy is like how many ways, like how many microstates, no? I have that give rise to the same object, like how many different ways I can construct the same. So what is that information? And this is this is the typical motivation, that there are no global symmetries. Now, as I said, like this is, the motivation is not the important thing. The important is the evidence that have been gathered based on ADS-CFT, string theory, and also recently all these works that show that the same replica wormholes that people are using to reproduce the page curve, the unitary page curve, are also breaking the global symmetries. Okay, so the intuition is that whenever you have topology changing processes, global symmetries are going to get broken, because in the end, a global symmetry is just characterized by a topological operator. So if topology itself can fluctuate, then we don't expect to be able to define an exact global symmetry, an operator that remains topological. Okay. So this was an intuition. Now, the way to understand, also to point back to define better what is the difference between global and gates in terms of the topological operators is about whether the charge operators are gauge invariant or not. So let me just to set notation, what is the definition? So as you all know, global symmetries are characterized by some unitary operator, which is topological, so it's conserved. The ordinary symmetries satisfy a group law, and they act non-trivially on some gauge invariant charge operator. So the generalization to higher force symmetries is that, as you all know, these operators now live in a d minus p minus 1 form surface, and the charged operators are localized on p-dimensional manifold. Okay, so the charges are carried by extended objects, in particular by p-dimensional dynamical branes. Okay, so what we are saying is that in quantum gravity, either we violate the first condition, so the symmetry is broken, meaning that the operator is no longer topological, or we violate the third condition, meaning that we still have some symmetry, some operator, but it doesn't act on any gauge invariant operator in my theory. Okay, so this is what happens, for example, for the electric charge. Okay, the electric charge is gauged, and the corresponding local operators are actually not gauge invariant, so it doesn't act on any gauge invariant operator, and that means that the symmetry is gauged. Okay. Okay, good. So if the second condition, if it's gauged, it's also going to mean that, since it does act, since it acts trivially, on all the gauge invariant operators, it's like the identity operator, so the operator becomes trivial. So the statement that there are no global symmetries, you can just summarize it as the statement that there are no non-trivial topological operators. Okay. Good. Okay, so now the typical, traditionally, like the expectation or the common law is that, okay, maybe it's nice, maybe you can get even some sharp proofs in some contexts, but it's not very useful because, okay, symmetries are not exact, but maybe they can be broken at a very high energy scale, so this is not going to be very constraining for the EFT. So it's not very useful for phenomenology. Now, in recent years, this trend is changing because we are realizing that this conjecture by itself can be much more constraining than expected, because thanks to all the recent developments regarding new generalized notions of symmetries. Because there are many string theory features that can be derived as consequences of no global symmetries. And even there are people that are trying to use this to test this notion of string universality, so where every FT consistent with quantum gravity can arise from string theory or not, or we are missing something with string theory. And I'm not gonna, I want to give you other examples about some features that can be understood as consequences of non-global symmetries, but I just want to point out that there is a lot of progress, which is very nice in theories with 16 supercharges, to classify the possible theories by requiring no global symmetries, anomaly cancellation, and supersymmetry. And this is becoming very useful to reduce the landscape, like to understand what theories in principle we think are consistent with quantum gravity because they don't have global symmetries, and then match with the string theory constructions. And at the moment, there is a perfect match. So we have string universality in dimension bigger than 7, which is a new progress of the past 2 years. So I have 2 tables in the backup slides in case you're interested to see exactly the progress. You can ask now or later, but otherwise I will just give you other examples in which I've been working on. Okay. So let's see how, the whole point is try to understand what happens when we break or gauge the symmetries. So just to be on the same page, let me just review quickly how you gauge or break these symmetries in practice. So for example, if you have some continuous symmetry, so I can define some current, just for simplicity, then we can just gauge it by coupling to a dynamical B field. If it's discrete, we can also do it with a discrete gauge field, but just to keep it simple in the slide, let me do it like this. So we couple to a dynamical field, and this is going to gauge the symmetries. Like, for example, if you have the 1,4 global symmetries associated to a Maxwell theory, you can add some B field, some 2,4 gauge field, and this is like the typical Stuckelberg coupling, which is gonna promote this global symmetry to be part of the gauge symmetry. Okay, it's like the global part. And then indeed, the operators that are charged under the symmetry are no longer gauge invariants because it's only the combined transformation of the A field and B field that leaves the theory invariant. Okay, so that's how you see that the symmetry is gauged. Another way to see it, in this case that we have a current, is that the current associated to the symmetry, which is just the field strength, becomes exact. Okay, so it's not only closed and it's not only conserved, but it's exact, meaning that it's going to be gauged. And that's why we will be able to transform, we have this Gauss law, like transform this integral volume on an integral in the surface. Okay, now what about breaking? So a global symmetry is broken if the operator fails to be topological. So this can happen, at least in string theory, we know 2 ways in which this typically happens. Either because, again, we have some coupling, some BF or Chern-Simon coupling, because the same coupling that was breaking the symmetry associated to the A field before, it's gauging, so the same coupling that was gauging one of the symmetries is breaking the other one. Okay, so you are introducing a new field that was gauging the previous symmetry, so you have a new P+1 global symmetry that actually gets broken, at least to a discrete group by this coupling. Okay, and you can see this because by the equation of motion, you can see that the current, which is the field strength, is not conserved anymore. Now, the other way is to add charge states. Like another way to get a non-conservation of the current is that we have some charge state on the right-hand side, and this is also going to break the symmetries. So if I have, for example, a 1,4 global symmetries, electrons are going to break it, okay? Because I have the electromagnetic current on the right-hand side of my conservation equation. So there are some cases in which we don't have currents, or it's not so easy to have a formulation in terms of the current. So it's much useful to think of the operators. And that's why instead of saying that the current is not conserved, what we can say is that the electrons are breaking the symmetry because now the charge operators, which are the Wilson lines, can end. Okay, so what is happening here is that you have some string charged under the 1,4 global symmetry, and this string can end because of the presence of the local operators that create the electrons, and therefore the symmetry operator is not going to be topological anymore. Okay, so let me show this pictorially, like in more detail. So just to make sure everybody understands. So if you have some symmetry, some global symmetry, remember we have some symmetry operator, which is this U, okay, that lives on a D minus P minus 1 surface, well, manifold. And then we have some charged operator, which is this V, which is a p-brane, okay? It creates some p-brane object. Now, if this operator is charged under the symmetry, it means that it links non-trivially with my symmetry operator, okay? So that if I shrink the operator and cross it, I'm gonna get some linking coefficient, which is, for example, a phase in the case of a continuous one. Okay. Now, if my charge operator can break, like for example, when we add the electrons and the Wilson lines can end, then I can just shrink this symmetry operator away. And since it's not crossing my charge, my defect is there is no phase, nothing happens. And this is a contradiction, meaning that the operator, I mean, this process would not be allowed. So meaning that the operator cannot be topological. Okay. So this is why, like, if the charge operators can end, the symmetry operator fails to be topological. And this is an important lesson to keep in mind for the rest of the talk. Okay, operators linking non-trivially with an endable operator cannot be topological. Any question? Okay, very good. So let's go now that I hope we are all on the same page. Let's go to the real meat. So let's see what are the consequences of breaking and gauging the symmetries. So I'm going to give you two things. I'm going to explain two consequences. The first one is completeness of the charge spectra. Okay, so let's start basic, and then we'll continue complicating the story. So let's consider just Maxwell theory, some U1 gauge field. So we have a one-fold global symmetry whose current is just the electric gauge field. We have the symmetry operator, the exponentiation of the charge, and we have Wilson lines that are charged under the symmetry. Okay, and they link non-trivially with a phase. Very good. Now, if we add charged states, electrons, now the Wilson lines can end. Okay, this is a summary of what we discussed before. And the symmetry is going to be broken. Okay, the question is whether we can completely break it or there is some remnant. Okay, now suppose that we add matter of charge n, since the Wilson lines are also on the representations of the gauge group. Only Wilson lines of charge n become endable. Okay, meaning that only operators that link non-trivially with them fail to be topological. In other words, those that link trivially, which means that they have this, they are labeled by this conjugacy class, by this alpha. If you come back, we come back here, whenever this phase is trivial, right? This is going to link trivially. So whenever alpha satisfies this, the symmetry operator links trivially with this Wilson line of charge n, and therefore remains topological. So this means that the one-fold symmetry is broken, but it's broken to a discrete group, a discrete Cn group, okay? Because there are some operators that remain topological. So the only way to completely break the symmetry is that you have matter for all possible representations. And here I am also thinking, I'm also considering multi-particle states, okay? So the important thing is just that you have the minimal states, the minimal charge, so that you can construct matter in all possible representations with multi-particle states. And therefore you will have all the Wilson lines for all possible representations will be able to break. Okay? Okay, so for the Maxwell theory, it's true that a complete spectrum is equivalent to have to avoid a global symmetry. And the question is whether this is a general lesson that we can extrapolate beyond Maxwell, okay, for any gauge group. Now, one can prove that it actually, the same argument that I gave you, it applies for any continuous compact gauge group, even if it's not U1, okay, any continuous compact gauge group, the same is going to happen. But it's not true in general for discrete or disconnected groups. So there was already a counterexample in the paper of Oguri and Harlow, which was based on a C discrete group, that they show that indeed, like you could have a complete spectrum and still have some symmetry that remains, okay? Or the opposite, like you could have an incomplete spectrum and no symmetries. So there was no one-to-one correspondence. So what I'm gonna argue is that, well, with another example, we are going to argue is that if we include now non-invertible operators also into account, then we can recover this one-to-one correspondence. Okay, so I'm going to do this instead of taking this discrete group. I think, I don't know, for me, I find more pedagogical to study the O2 gauge theory. So this is some disconnected group. And here is very easy to understand what's going on and how these non-invertible operators come into play. Okay, so let's see the example. So O2 gauge theory is a U1 gauge theory in which we are also gauging charge conjugation. Okay, so you can decompose O2 like this, and you have different representations, some fundamentals, and then you also have the determinant, okay, which is in the adjoint. You have, now we're gonna have Wilson lines and all these representations. Good. Now, symmetry operators, I mean, we can construct the symmetry operators for O2, starting with the U1 gauge theory. We just have to take into account this gauging of the charge conjugation, okay? This means that the symmetry operators, I mean, that are in general, no, are labeled by a phase in U1. They are only going to be gauge invariant for 0 or pi, and otherwise they are not gauge invariant because they are not invariant under the C2. So what we have actually is not a U1 one for global symmetry, but we have a C2 one for global symmetry expanded by these two topological operators. And this is the way to analyze this or to determine this in general is that the one for global symmetry, as probably you know, it corresponds to the center of the group. Okay. Any questions so far? Good. So now let's add matter and see if we can recover this one-to-one correspondence between a complete spectrum and no global symmetries. Now, suppose that we add charge matter. If we add charge of even charge, matter of even charge, then this is going to preserve the C2 one for global symmetry, so nothing happens. That's not enough. Good. I need to add more things. If now I have to add odd charge, and this is going to break the C2 one for global symmetry. Okay. Now, the problem is that if I add charge equals 1, this is fine. The spectrum is going to be complete, and I'm completely breaking everything. So I have a complete spectrum and no global symmetries. But if I add, for example, only matter of charge 3 and the multi-particle states, then the spectrum is incomplete because I don't have the charge 1. But this is enough to break the symmetry. So this is a case in which you have an incomplete spectrum, but there are no global symmetries. Okay, so this side of the correspondence doesn't work. Okay, any question? Good. So what is going on? I mean, why is this happening now and it didn't happen for the Maxwell theory, no, for the U1? Well, what happens here is that in the case of the U1, if we add charge, a matter of charge 3, what happens is that there should be some topological operator that remains topological, which is labeled by this alpha, and would therefore generate a C3 global symmetry. But the problem now is that this global symmetry that would generate is not gauge invariant. I mean, this operator is not gauge invariant, and that's why it's not there, and there is no symmetry left. However, there are other operators that remain topological, which are the gauge invariant combinations of this labeled by 2 pi over 3 and minus 2 pi over 3. So this combination is invariant under the C2, the gauge conjugation. So this is a topological operator in my O2 gauge theory, which remains topological when I only have matter of charge 3. So this is the operator remains topological, and the only problem or the interesting feature is that this operator is non-invertible. Okay, because if you, there is no, it doesn't have an inverse, no? Like if you multiply by the inverse, you get the identity plus more things. So the summary is that if the spectrum is incomplete, the one for global symmetry may be broken, but there are still topological non-invertible operators that generate a non-invertible symmetry. So if we also require the absence of all these non-invertible symmetries, then we recover the one-to-one correspondence between no global symmetries and completeness of the spectrum. Any question? Okay, so this is one example. The point is that we want to prove this for any gauge group. So this is what we do in the paper. So, I mean, just to make clear, so the non-invertible symmetries that also probably you all know about, the only difference with the definition I gave you before is that now they do not satisfy a group law, but some more complicated fusion algebra. But the rest is the same, okay? And then the point is that this linking coefficient can be more complicated. It's not just a phase, no? It can be some matrix, more complicated object. But again, whenever this is non-trivial, then I will have some non-invertible symmetry. Okay, so the proposal that we have is that this always works like this one-to-one correspondence between not topological, including non-invertible operators and a complete spectrum, meaning that all extended charged operators can end, should work in general. And what we can do in the paper is to prove a simplified version in the sense that we separate electric and magnetic and consider the electric case independently and the magnetic case independently. Okay, so what we can prove is that for any compact gauge group, even if it's discrete or disconnected, which is only coupled to matter, I only have these electric symmetries and that's it. Then the absence of topological, including non-invertible Gukov-Witten operators, is equivalent to requiring that all the Wilson line operators can end. So you have electric completeness. I'm going to outline the proof briefly, and then we'll just go to the second consequence for the rest of the talk.
So you also don't allow for anomalies, Toft anomalies?
No, exactly. No, not here because I just have pure gauge theory. So I don't couple these to other fields or like typically, I mean, to have Toft anomalies, right? Like typically you have something.
Oh, you can have a Toft anomaly in pure gauge theory too, right?
I'm thinking like, for example, when you couple to the B field or things like this, but maybe what you have in mind, for example?
What do you mean? So for example, spin gauge group with vector matter, spin 4n+2 with vector matter has, sorry.
Okay,
you
as long as
you gauge that has a two group and then gauge it, so you can get mixed anomalies. And,
yeah, okay, but you have a two group. Okay, so that's the point. So here, for this proof, the assumption or the starting point is that the only way to break the symmetry, so to render the operators non-topological, is that they link non-trivially with some endable Wilson line. If there is another way in which they can become non-topological, which can happen sometimes also when you have a higher group structure or other things, then you have to generalize this proof. So what matters here is not necessarily whether it's anomalous or not, but what matters is whether the only way, I mean, in your theory, to render the operator non-topological is by linking with an endable Wilson line. Like there is no other ingredient, nothing else. So typically it means that you have like a pure gauge theory only with matter.
okay.
Like for example,
But
like
pure gauge theory with matter can have.
Yeah, so that's why I say higher group structure. It's
higher group structure has nothing to do with non-topological, right? These are still topological operators, just have some.
But for example, like
fusion.
I'm saying this because there's one example, like the C2 cross C2 gauge group in 3 dimensions. I think we studied this. If you just have matter, like you just have the gauge theory and matter, has like some, because there is another way in which the operators can become non-topological, because it's not only that they link with lines, but you can also have some surfaces and things get mixed in a more complicated way, which I think is pointing out that there is actually some two-group structure there. And then you have to generalize the proof, because here, yeah, it's like maybe there was already some operator that was not topological to start with, so you have to start with a different set of operators. So whenever I hear two-group structure, I think that I have to revisit it because I'm not sure if it's gonna play or not. The important thing is that, I mean, it could be that there are some cases in which already some of the operators that I'm going to consider are already non-topological because of the linking that they have, and you have to check that. Here I'm assuming that everything is topological, and I want to see that the only way in which everything becomes non-topological is to add the complete spectrum. There could be other ways, and that's why one has to check in those cases.
But a two group has completely topological, like everything is topological, right? Both the zero form and one form symmetry generators. There isn't like something that breaks the topological nature of them. It's just that they have some non-trivial.
I know that in the case of the C2 cross C2, it happens that there are some operators that are not topological. Maybe it's not a general thing. It could be that sometimes you have a two-group structure and still everything is topological, and then this proof will apply. I just don't know how to characterize exactly when it happens and when it doesn't. So yeah, that's.
Good question. The slide says valid for general compact gauge groups in any dimension coupled to matter.
Any dimension, yeah.
But I thought Sakura's point is there are examples of theories in that class.
I think we will move it to the discussion, Matt. Okay. Yeah, let's move it to the discussion because that's exactly my point, that there are examples which are of this type, which have higher groups or which have mixed anomalies, and then it's kind of a question, does this still apply? Because you sort of also taking out things that could mix electric magnetic. So,
okay, let me give you the proof and then we'll see if the proof still applies or not. Okay, so yeah, so we want to break all these one form global symmetries, which are characterized by some Gukov-Witten operators. So they are codimension 2 operators, and they are labeled by the conjugacy classes, and they are topological if they belong to the centralizer of the gauge group and is connected to the identity. Now, the charge operators are Wilson lines. They are labeled by representations of the gauge group, and those that are built from the joint representation are already endable. Okay, it's like they can end on the gluons, but those that are not built from that joint are not endable in pure gauge theory. So that's what I mean. So these are the assumptions, if you want, that I'm taking. Like these are the charge operators that I have that are not endable without matter, and these are the symmetry operators that are topological without matter, that belong to this centralizer. If these two conditions still work, then everything I'm going to say still applies. If some of these changes because there is another way to bring some of these operators non-topological, then I mean one has to revisit if the one-to-one correspondence still holds.
Sorry, very quick question. G0 is what? Sorry.
The identity.
The identity component.
What is the identity component?
The connected component.
What is connected to the yes.
Thank you.
Okay. So just quickly, so the point what we have to show is that what we have learned is that a Gukov-Witten operator stops being topological if it links non-trivially with an endable Wilson lines, meaning that this is the linking coefficient, so meaning that the character of the representation is non-trivial. Okay, it's different from the character for the identity. So now, suppose that we add matter in some representation rho, okay, so that this Wilson line becomes endable. What we want to prove is that the spectrum is incomplete if and only if there is a non-trivial element of the group whose character is equal, okay, to the identity, so it satisfies this for all endable rho. Okay, so this means that we want to prove that the spectrum is incomplete if and only if I still have some operator that links trivially with all these endable representations so that it remains topological. Okay, so that if it's incomplete, I must have some global symmetry and vice versa. Is it clear? So this is nice because this you can just reduce it to a group exercise, right? A group algebra exercise. You can just show, you just have to show if in general I mean, what are the characters of the different representations and whether you can find this non-trivial element or not. And this is what we do. So just quickly, the point is that if you take rho as a direct sum of all matter and adjust representations, then there are two cases. It could be that rho is faithful or not faithful. And this is going to imply that we have a complete or an incomplete spectrum. And if it's faithful, then one can prove there is some lemma which shows that the character in this row, in this faithful representation, satisfies this, meaning that indeed only if the spectrum is incomplete, I can find some element that satisfies this and I have a global symmetry. While if the spectrum is complete, then I don't have any global symmetry left. Okay. And here this is including non-invertible symmetries because I'm just considering all possible elements of the all possible conjugacy classes. So this is basically the proof. This is to show this electric completeness in this case, which we just focus on this electric case, and there is no mixing. Okay, there is no another way to break these symmetries. Now you could wonder, what about the magnetic symmetries? The magnetic story is actually complicated for the case of these connected groups. Because I mean, if it's a continuous group, then it's fine. Like then it's equivalent to the electric part that we just did. You have a D-3 for magnetic symmetry broken by monopoles, and it's the same story. But the point is that the top operators, that's the symmetry operators of this magnetic symmetry, they are labeled by this quotient, and whenever this axion of pi 0 is non-trivial, it means that the magnetic symmetry itself becomes non-invertible. And yeah, how to study this? I mean, we have not done it yet. It's something would be nice to do it in the future. One way to proceed is try to understand better this duality, no, for the disconnected groups. But what we have done is a small part of this, which is to consider the D-2 form symmetries that are labeled by pi 0 itself. Okay, so these are the symmetries that are generated by the Wilson lines whenever the Wilson lines are topological. So it's like inverting the role of the Wookhoff-Witten and the Wilson line operators, so that the Wilson line operators are now generating the symmetry, and the Wookhoff-Witten operators are the objects charged under the symmetry. So these Wookhoff-Witten operators are going to create twist vortices like cosmic strings. And then we can show again that we can show in the paper that there is a one-to-one correspondence between no topological Wilson line operators and Wookhoff-Witten operators being able to end, which means no non-invertible D-2 for global symmetries and completeness of the twist vortices. Okay. Now, of course, the next step is to mix electric and magnetic, to consider more general groups in which there is, I don't know, maybe some higher group structure, which in practice is kind of mixing the two things. Okay. So what I'm going to do for the rest of the time is to give you, to give you some examples. So the point is that without mixing electric and magnetic, we can give these general proofs. When mixing electric and magnetic, we don't have a general proof, but we can study examples. So what we have done just to study some examples and see at least what happens and get some intuition of what we would expect, and that would be nice to generalize in the future in general. So yes, I'm gonna give you an example which comes together with the other consequence that I wanted to talk about, which precisely comes when you mix both symmetries. Okay, now just before one slide, let me say that this is, I mean, if you are interested in quantum gravity, this is also interesting because this completeness of the spectrum and no global symmetries were in principle two independent Swampland conjectures that now it seems that they could follow from each other if we allow for this generalized notion of symmetry, including non-invertible operators. So it goes along the lines of try to unify all the Swampland conjectures and reduce everything to the minimum set of principles that would reproduce everything. Okay, so let's go to the consequence 2, which is precisely when we are going to have these Chern-Simon terms or something that mixes the different symmetries. And we're gonna see what changes in the story of the completeness, and also how we can derive actually many new features and constraints in the dynamics from this. Okay, so let me just take an example and exemplify this with an example, which is just axion electrodynamics. Okay, so here we have our gauge theory, but now it's coupled to some axiom. Okay, we have this coupling. And you can enumerate the different symmetries that you have. Okay, so we have a 1-4 global symmetry associated to the gauge field, which is broken precisely because of the presence of this coupling. So this is what I said that changes when you have these couplings, because now this symmetry is broken even if I don't have electrons in my theory. Okay. I also have a magnetic D-3 for global symmetry, which is exact if I don't have monopoles yet. Okay, if I don't have any matter. And I also have a new symmetry, which is a D-5 for global symmetry, which is what we call a Chervil symmetry, which is given by the product of FHF. Okay, so this is another current which it's generating a symmetry, it's conserved, and actually what happens here in this theory is that it's gauged. Okay, because you can see that this current is exact by this equation of motion. Okay, so this symmetry is gauged by the axiom. Now, if we want to get rid of all the possible symmetries, we need to add monopoles. Okay, this is the one that remains, and then we can see what happens. Okay, so let's add monopoles. Now, in the presence of monopoles, which can, for example, come if I have like the SU2 and I break to the U1 and I have the typical Topologocial monopole, then the magnetic symmetry gets broken, but also this D-5 for symmetry that I had before, the span by FHF, it also seems to be broken now. So this can be puzzling, it can be confusing, because I just told you that the symmetry was gauged. So that means that there is an anomaly, right? Like if you have some symmetry that the current was exact, now you can just take another derivative here, this should be 0. But since this is broken, this is non-zero, so this is just showing you that there is an anomaly. You are trying to gauge a symmetry that is broken or break a symmetry that is gauged and is inconsistent. So we should try to fix it. And the way to fix it is that you must define, the theory must have some more ingredients. So you must have some improved current in which beyond FHF, you also have some other four-form contribution that it's going to come from degrees of freedom living on the monopole. Okay, so when adding the monopole cannot come alone. If it comes alone, then you have this anomaly. But it's like doing anomaly inflow now. Like you need to have some worldvolume degrees of freedom living on the monopole that you can just derive exactly what it is just from all these equations of the symmetries. You can check that, for consistency, we know what the derivative of this contribution should be so that it cancels and everything is consistent. And we know also that should be localized on the monopole, and it must have, since the derivative is f, it means that omega-4 has to be proportional to A, to the gauge field, but this is not gauge invariant alone. So it must come with another piece so that everything is gauge invariant. And this means that you must have some scalar living in the monopole. And actually you can understand the scalar as the Goldstone degree of freedom from this 1-4 symmetry, which is broken, and even if it's gauge in the bulk from the point of view of the monopole of the localized theory, it's like a global symmetry, so it gets spontaneously broken, and this is like the Goldstone field. So just from consistency of requiring the absence of global symmetries, what you can derive, you can reinterpret the existence of this scalar localized on the monopole, which is a very well-known degree of freedom. When you have this Topologocial monopole, you can study the different zero modes, and you can see that this is a zero mode that exists, and it's precisely the one that is implementing the Witten's effect. Okay, so it's like you can reinterpret, derive again its existence from all these arguments of no global symmetries. And since it's implementing the Witten effect, it means that it's inducing electric charge on the monopole. Okay, so let's recap what is happening. So we had originally some magnetic symmetry that we needed to break. We had monopoles. And even if the electric 1-4 symmetry was already broken, so we didn't need to add electrons, the Wilson lines wouldn't end. When adding the monopoles to break the magnetic symmetry, now the Wilson lines become endable by the Witten effect. So you recover this one-to-one correspondence between no global symmetries and endable operators. Okay, so now you have again some electric degree of freedom, even if you didn't require this from the beginning. So two messages. First, the absence of global symmetries in the presence of Chern-Simon terms requires the existence of localized charge degrees of freedom always in the objects. This is just by the symmetry, by consistency. And also, one recovers the one-to-one correspondence between no topological operators and endability of all operators. It's just that you have to take everything into account. You cannot just split, of course, electric and magnetic. Like by requiring to break the magnetic symmetry, in the end, you're also going to generate the electric degrees of freedom. And you have to check at everything at once. Okay. Okay. So one can play, I mean, this was just an example, but you can study many different types of examples. We study some of them in these papers. You can study more, like try to try to give more general proofs. Like for example, you can play the game of starting with supergravity of type 2A and checking like how much you can derive from string theory just by requiring the absence of global symmetries. Okay, so before I give you an example that you derive the existence of these degrees of freedom on the monopole, so how much we can derive from string theory and all the rich structure that we have of brains and so on, just from starting with supergravity and requiring no global symmetries. And it turns out that you can actually derive a lot because whenever you have all these gauge fields and all these Chern-Simons and so on, you have many types of symmetry. You can construct all these Chern-Wire symmetries with products of the different gauge fields. And if you want to require the absence of all these new symmetries, you can reproduce the spectrum of type 2A. So whenever you consider just a current with one F, like the typical electric or magnetic one, then you are going, I mean, in order to break the symmetry, you need charged objects. This is like the story of completeness that we saw. But whenever you start considering higher rank products, so you consider F with F, now you are going to require the existence of localized degrees of freedom on the brains. And if you continue like studying now the new currents that appear with these new degrees of freedom, then you are also going to derive the existence of localized degrees of freedom on the intersection of the brains, and so on and so forth. So that it seems that, yeah, like all this rich structure of brain, worldvolume fields, and all these typical top-down features of string theory might be more general than expected. Like you can just try to derive it from the absence of all these new higher forms by global symmetries. Okay, so just to finish, we can just want to give one last example of this type associated to this F with F. So you can also interpret the existence of the axions this way. Okay, so I told you, yeah, that when you have F with F, this is also some symmetry that you must consider, and in quantum gravity you should break it or gauge it. So the problem is that these symmetries are very difficult to break completely, okay? Because sometimes, for example, you don't have monopoles to do it, right? Like before I gave you an example in which we had some monopole and then you have these degrees of freedom, the monopole and so on. But depending on the gauge group, like for example, if it's simply connected, maybe we cannot have a monopole. So how do we break these symmetries? And we couldn't think of a way to do it. So the only way that we could think of and that we found in string theory is that we cannot break it, so we must gauge it. And yeah, in all the examples we could find, this was always what was happening, that whenever we have this non-abelian these groups. In the end, you need to gauge the symmetry, so you need to have an axion that couples to this FHF to get rid of the symmetry. So you can try to interpret also the presence of axions this way. And it's also interesting because typically for the strong CP problem in QCD, there is this axion quality problem. Like people wonder, like how, okay, if you just have an axion coupled to the QCD, instanton is fine, it looks, everything works very nice, but how do you guarantee that this axion doesn't couple to other things such that it does not spoil the QCD minimum, okay? So this is the axion quality problem. That actually makes many people in Fino like to think of other alternatives beyond the axions for the strong CP problem. But it's interesting that from this perspective, if I have other things that couple to the axions, I'm also introducing new types of symmetries. So the axion is only going to gauge the combination of all of it, like one linear combination, and all the other linear combinations should be broken, meaning that there should be a way to transform one instanton charge into the others, because otherwise there is some symmetry that remains in your theory. So this is something to study also in the future, but it would be nice to see if this correlation that it seems that quantum gravity is imposing to get rid of all the symmetries, so that you should be able to transform one charge into the other, so there is like the symmetries get broken, could introduce some correlations between the phases and the axions of the different contributions, such that in the end you don't have this axion, or at least it ameliorates the axion quality problem. Okay, so this is something to consider. And the last thing to consider also, like I'm also putting you here like open questions to think about, is that this D-5 for global symmetry I'm talking about in 4 dimensions is a bit exotic because it actually corresponds to a -1 for global symmetry. Okay, in higher dimensions it's a usual symmetry, we can understand it very well, but in 4 dimensions it's a -1 for global symmetry. So you could ask whether this makes sense. What does it mean a -1 for global symmetry? No? How can we properly formulate this? And this is something I find very interesting because these -1 for global symmetry are present all the time in string theory, actually. Like they correspond to have some top 4 current, and it's like, I mean, if you have a -1 for symmetry, it's like having some free parameter that label your vacuum. So now -1 for symmetry, the charge is going to be carried not by some p-brane, but by the entire space-time. So it's like a label for the vacuum. And the absence of -1 for symmetry is equivalent to the statement that there are no free parameters. So the typical law that there are no free parameters in string theory, you can rephrase it as requiring the absence of -1 for global symmetries. And you could say, okay, but how do I make sense of gauging or breaking these symmetries? Well, gauging is also something that happens all the time in string theory because it completely makes sense to ask if this top 4 current is exact. Okay, this is a well-defined question, and like all these examples of axion monodromy, like whenever you have axions that are stabilized by fluxes in string theory, this stabilization of the fluxes is gauging the -1 for symmetry associated to these fluxes. Okay, so all these fluxes are going to have -1 for symmetries, and whenever they couple to the scalars, these symmetries get gauged. Okay, but you can also break them, and break them seems confusing because this is a top 4 current, so it seems that it's always conserved. So what does it mean to break this -1 for symmetry? What does it mean to have a -2 object? No. The way that we are starting, that we are trying to formulate better, is that breaking these symmetries is equivalent to find some path in the space of field configurations, not in space-time, but in the space of field configurations that allows you to deform the charge, like to change it. Okay, so it's like, I mean, at the moment, I think the best formulation for this is actually to think of cobordism. You just have to think of the top form cobordism group, like in 4 dimensions omega 4, and it's about whether this group is trivial or not, like whether there is some path in configuration space that allows me to change this parameter, and whether I can connect these 2 EFTs with different labeled by different values of the parameter by some domain wall that maybe change topology or whatever, but some domain wall that interpolates between the two EFTs. So this is what would mean to break this -1 for symmetries. Okay, so with this I finish. So let me just summarize. I mean, we think that global symmetries can be broken, should be broken or gauged. Regardless of this, it's interesting to understand how they can be broken or gauged, because we can reinterpret and also discover new phenomena from requiring this. So it's a way to classify the landscape and the possibilities that we have. We have seen that completeness of the spectrums is to be correlated to breaking the symmetries. And we have proved this for some particular setups. And when you add Chern-Simons terms, then the story gets more complicated. It seems to still work, but we are missing some general proof. But you can also argue, this is very interesting, because then you can also argue for the existence of localized degrees of freedom and axions, and reproduce many familiar phenomena in string theory from this language of no global symmetries, which makes you wonder whether maybe all these top-down features might be more general features of quantum gravity, if we think that no global symmetry should be a general feature of quantum gravity. So with this I finish, and I had here also a final comment, something I'm thinking about, so I'm also happy to discuss if you wish. We are wondering if the opposite is true, in the sense that we say that quantum gravity cannot have global symmetries. Could it be that UV complete QFTs, like CFTs, all we have global symmetries, like topological operators? So there is like a disconnected set of EFTs that can be either UV completed in quantum gravity or in CFTs. And so far we have not found any counterexample, but it's something to think about. Thank you for your attention.
Okay, thanks very much for this nice talk. Are there any questions, apart from the ones that we had and we probably want to continue discussing, but maybe there are some questions beforehand on other parts of the talk?
Can I ask a question? Is there a formulation of the completeness hypothesis for non-Lagrangian theories? Something that one can say without going to the Coulomb branch?
In principle, the only formulation that exists is that you must have physical state for all possible representations of the gauge group.
Yeah, so you don't have a gauge group?
Yeah, exactly. So that's, I don't know. I don't think nobody has thought about it yet. I would say that's probably the way to go is precisely, like to think of the operators, like whether all operators are endable in your theory. Because this is the way, instead of saying no global symmetries, we say no topological operators. Instead of saying complete spectrum, what we say is that all operators should be able to end, to break. Mm-hmm. So I think this should be the way to go without a Lagrangian or anything like that.
So you're saying there's no,
all operators should be able to end.
Okay.
Which also, I think is nice because, this is just like some vague comment, but I like this formulation because it also connects with the coordination. Because if you say, all operators should be able to end, then it's equivalent to the completeness hypothesis and so on. But also if you generalize this even to the entire spacetime and say that the entire spacetime should be able to end and have a boundary, this is like the coordination conjecture. So it seems that the way to formulate everything just with one sentence, like no global symmetries, coordination conjecture, completeness hypothesis, and so on, is to require that like everything should be able to end, like to have a boundary, in a sense.
Right, very nice. Thank you.
Any other questions? And maybe I suggest we thank Irene again, then we stop the recording and we discuss the 2 questions that came up during the talk. So thanks again.